Chapter 5 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. The Romance of Modern Engineering by Archibald Williams. The Tower Bridge. Less imposing as a structure than the giant conqueror of the Forth is the new bridge that spans the Thames a short distance east of the Tower of London, from which it derives its name. The Tower Bridge is, however, of such importance and interest, both on account of the problems that it has solved and from the manner in which it has solved them, that this great framework of metal and masonry, so familiar to the Londoner, deserves inclusion among the chief engineering feats of modern times. The general outlines of the bridge, being so well known, need little detailed description. Technically, it is a three-span bridge, the two outside spans of the suspension type carried on the stout chains that pass at their landward ends over abutment towers of moderate height to anchorages in the shore, and at their river ends over very lofty towers, themselves connected at an elevation of 143 feet above high water level. Extremely powerful ties, borne on the connecting girders, unite the two pairs of chains, making the suspension spans to support one another in a horizontal direction. The Tower Bridge. The central span has two footways and one roadway. The high-level girders bear the upper footway, reached by two hydraulic lifts situated in each of the main towers. The most notable feature of the bridge, unless we accept the unique combination of steel and masonry work in the towers, is the method of enabling traffic, pedestrian and vehicular, to cross the 200-foot space between the towers at the level of the roadway of the two outer spans. History repeats itself in engineering as elsewhere, and as an example, we see here a reversion to the idea of the drawbridge that shut off the medieval fortress or town from the hostility of the outside world. Principle apart, however, it is a far cry from the wooden platform heaved laboriously aloft by creaking chains to the massive 1200-ton steel leveraged noiselessly by the unseen energy of hydraulic engines. Before entering into details of construction, it will be interesting to glance for a moment at the antecedent of this latest born of Thames bridges, the reason for its erection, and the considerations that cast it into its present form. Let the reader take a map of London and fix his eye on Blackfriars Bridge. A line drawn due north and south through the bridge would approximately bisect the metropolis. A steamboat travelling westwards from this point passes in succession under Waterloo, Westminster, Lambeth, Vauxhall, Chelsea, Albert, Battersea, Wandsworth, and Putney bridges, 9 in all, open to vehicular traffic. On an eastward journey of equal length, it would, however, have to lower its funnel for but two, the southward and London, assuming the Tower Bridge to be still in the future. Yet both banks are thronged by some of the most densely populated districts of London, so near each other and yet so far for want of means of communication. A further reference to the map shows us why things should be so. This is a region of docks and wharves, the latter reaching up to London Bridge, from which we have often watched the unloading of cargoes. The engineer called in to effect a compromise between the crying needs of road traffic on the one hand and the equally important interests of river traffic on the other, is able to suggest several methods of cutting the Gordian knot. First, a low-level bridge with an opening for vessels through it. Second, a high-level bridge with inclined road approaches. Third, A high-level bridge with hydraulic lifts at each end. Fourth, a tunnel under the river with inclined approaches. Fifth, a tunnel with hydraulic lifts at each end. Sixth, a ferry. Of these, the first would be most convenient for the landsman but most inconvenient for the sailor. The second and fourth necessitate very costly approaches. The third and fifth, continual blocks in the traffic, and as regards ferries, they are at best but very poor substitutes for a bridge. Among the many plans submitted since 1867 for a bridge, one is particularly noticeable for its originality, that of Mr. C. Barclay Bruce. He proposed a rolling bridge to consist of a platform 300 feet long and 100 wide, which should be propelled from shore to shore over rollers placed at the top of a series of piers 100 feet apart. The platform would have a bearing at 2 points at least, and according to the designer's calculations, make the journey in 3 minutes with a freight of 100 vehicles and 400 passengers. Another engineer, Mr. F. T. Palmer, proposed a bridge which widened out into a circular form near each shore, enclosing a space into which a vessel might pass by the removal of one side on rollers while traffic continued on the other side. As soon as the vessel had entered the enclosure, the sliding platform would be closed again, and that on the other side be opened in turn. In 1878, Sir Joseph Bazalgette, engineer to the Metropolitan Board of Works, recommended the construction of a bridge that should give a clear headway of 65 feet above Trinity high water level, but a bill brought into Parliament for power to build it was thrown out on the ground that the headway would be insufficient and on account of the awkward spatial approaches. To avoid wearying the reader with a list of projects, we will pass straight on to that of Mr. Horace Jones, the late city architect, who in 1878 was asked to report upon the various projects of Sir Joseph Bazalgette and make suggestions on his own account. He maintained that as a high level bridge would not give satisfaction, a structure of the same level as London Bridge, opening at the centre by means of hinged platforms or basculars, might be advantageously employed. From his design had sprung that of the Tower Bridge, the joint work of him and Sir J. Wolfe Barry, which provides a central opening of 200 feet clear and a headway of 135 feet. An act for its construction having been passed in the autumn of 1885, contracts were let for foundations of the piers and abutment towers up to the level of 4 feet above high water mark. On June 21, 1886, the then Prince of Wales laid the foundation stone. The masonry piers on which the main towers stand are remarkable for their size, 100 feet wide by 205 long, which exceeds that of any in the world with the exception of those of the Brooklyn Bridge. The piers being but 200 feet apart, the engineers who were under agreement to leave a clear way of 160 feet between them could not build both simultaneously as a whole, since the scaffoldings would have narrowed the opening beyond legal limits. They therefore adopted a system of small caissons which should be sunk so as to form a broad wall round the area of the pier and enclose a space of 34 by 124.5 feet to be dealt with as soon as the exterior caissons were in position. On the north and south sides of each pier, 4 caissons were sunk 28 feet square and 2.5 feet apart, each end of the rows being joined by a triangular caisson. While one pier was in course of construction, the shoreward row of caissons for the other pier was also sunk, thus saving time without obstructing the river. Reference has been made in the previous chapter to the sinking of caissons, so it need here only be stated that at the Tower Bridge no pneumatic caissons were employed but only the open variety. Divers cleared away the gravel and mud until a caisson had descended such a distance into the stiff London clay at which it was thought safe to pump out the water at low tide, and then navies were turned in with pick and shovel. At a depth of 19 feet, the caissons were undercut, that is, the workers burrowed beneath their lower edges into the clay for a distance of 5 feet horizontally and 7 feet vertically. The undercutting proceeded in sections filled with concrete in succession so that the caisson should not be left unsupported. When all the 10 external caissons had been sunk and filled in, the narrow spaces between them were also filled, and the interior enclosure pumped dry and excavated. Finally, there emerged from the water a couple of gigantic piers of concrete, granite, and bricks able to withstand without settlement a load of 70,000 tons. Their cost was 111,122 pounds. The contract for the steelwork in the superstructure was let to Sir William Arroll and Company of Glasgow, who, as the reader will remember, had already taken an important part in the construction of the fourth bridge. Before any metal work could be placed in position, it was necessary to erect stagings from the shore abutments to the center piers. This work occupied some months, and when it was completed, operations at once commenced on the main towers. Each tower consists of four octagonal columns connected at a height of 60 feet above the piers by plate girders 6 feet deep, across which are laid smaller girders to carry the first landing. 28 feet higher is the second landing, similarly constructed, and above that, at an equal distance, the third landing leading to a high level footway. The columns each rested on massive granite slabs previously covered with 3 layers of specially prepared canvas to make the pressure even and the joint watertight. They were keyed to the bedstones by great bolts built into the piers. The first length of column plates having been riveted in position by hydraulic riveters, the second length was added by means of a crane placed on the piers, and when the crane had been raised aloft on special trestles, the third length followed. The first landing served as a platform from which to build upwards in like manner to the second, which in turn became the base of operations. All four columns in each tower were braced diagonally to resist the wind pressure, calculated at a maximum of 56 pounds to the square inch, or several times greater than has ever been registered in that locality. The columns finished and the top landing girders in position, the workmen attacked the high level footway. This was built out from the both towers simultaneously on the overhang principle. First, the portions of the cantilevers immediately over the towers were erected and anchored to the shoreward columns. Then cranes were placed on the completed portions and moved forward to add fresh plates until the cantilevers had reached the point where the central suspended girders began. As at the fourth bridge, this was built on the cantilever ends to which it was attached by temporary ties, and when the center plates had been made secure, the ties were cut, allowing it to ride free at each extremity. Throughout the construction of the upper footway, the greatest care had to be observed to prevent rivets, fragments, and tools falling into the river below the peril of passengers on passing vessels. Along the upper boom of the footway run the great ties connecting the suspension chains at their river ends. Each of the two ties is 301 feet long and composed of 8 plates, 2 feet deep and 1 inch thick, terminating in large eye plates to take the pins uniting them to the suspension chains. The construction of these chains was one of the most interesting and at the same time most delicate parts of the whole undertaking. Each chain is composed of two parts or links, the shorter dipping from the top of the abutment tower to the roadway, the longer rising from the roadway to the summit of the main tower. The links have each a lower and upper boom connected by diagonal bracings so as to form a rigid girder. They were built in the positions they had finally to occupy, supported on trestles, and were not freed until they had been joined by huge steel pins to the ties crossing the central span and to those on the abutment towers. In order that the reader may have a clear conception of the action of the ties and chains, we will personally conduct him from end to end of the series. At the north end of the bridge is a huge mass of concrete surrounding an anchorage girder 40 feet long, 4 feet wide and 4 feet deep, to which is attached a land tie springing up to the shore edge of the abutment top. At the anchorage end, the tie is joined by a pin 2 feet in diameter to the girder and at its upper end to the horizontal links crossing the abutment tower. The tie is built up of 12 plates 21 inches wide and nearly an inch thick. The link plates are 5 to 5.5 feet wide and 7/8 inch thick and 22 feet long. At each end, they rest on roller bearings moving over 3-inch steel plates very carefully leveled. Then comes the short link of the chain, attached by eye plates and a steel pin 2.5 feet in diameter to the tie and also to the lower end of the long link, at which point both are joined to the girders of the roadway. Passing up the long link, we reach the top of the towers and note the great pins and roller bearings at each end of the 301-foot ties. Then down the south long link to the roadway, up the short link and over more roller bearings to the last section of the series, 12 plates 35 inches wide secured by rivets to the south anchorage girder, which is of larger dimensions than its northern fellow. This arrangement of chains, links and ties permits a slight amount of horizontal motion to compensate the stresses of unequal loading on the two suspension spans and the alterations in the length of the metal connections in varying temperatures. Roller joints are also made in the flooring of the side spans at each end and at the junction of the links to allow for longitudinal expansion and contraction. The boring of the pinholes was a matter of great delicacy and considerable difficulty. The holes in the eye plates of ties and chains had been cleared to within half an inch of their final diameter before leaving the contractor's works at Glasgow, and the finishing touches were added when the plates were in position. The labor of expanding out the holes to their full diameter was equivalent to boring a hole 2 feet 6 inches in diameter through 65 feet of solid steel, and most of this boring had to be done in somewhat awkward positions at the top of the main towers and abutments, whither it was necessary to transport engines, boilers, and boring tools. The fixing of these generally occupied as long a time as the actual boring, since the greatest accuracy had to be observed throughout the process. The roadway of the suspension spans is carried on cross girders 61 feet long, weighing 22 tons. At each end, they are connected by 6-inch pins to the suspension rods hanging vertically from the chain links. The rods are from 5.5 to 6 inches in diameter and furnished with a screw coupling at their centers to enable the accurate adjustment of the girders to the true level of the roadway. Before leaving the works, each rod had been subjected to a tension of 200 tons so that of their sufficiency there can be no doubt. Longitudinal girders of smaller section were then laid on the transverse girders, and on these again corrugated floor plates, afterwards filled up with concrete to form a slightly convex surface over which wood paving blocks were placed. We may now turn our attention to the central span of the roadway, which forms perhaps the most interesting part of the whole structure. Each bascule or leaf of the drawbridge consists of four parallel girders, 13.5 feet apart and about 160 feet long. When lowered, it projects horizontally 100 feet towards the opposite tower, spanning exactly half of the opening. The point of balance is a solid pivot, 1 foot 9 inches in diameter and 48 feet long, that passes through the girders 50 feet from their shore ends. The pivot is keyed to the girders and rotates on roller bearings carried by 8 girders crossing the piers horizontally from north to south, themselves borne on the girders under their ends. The chief difficulty attending the erection of the bascules resulted from the condition compelling the contractors to leave a clear way to 160 feet between the towers. Under other circumstances, the girders might have been completed before being brought into line and connected together. As it was, the engineers first built the portions on the shore side of the pivot, added a short section of the riverside steelwork, and launched the incomplete girders from the main stage close to the piers into the bascule chambers. A temporary steel mandrel was inserted to carry their weight while they were turned into a vertical position, and then withdrawn to make room for the permanent pivot weighing 25 tons. The outer ends were added to until a point 53 feet from the pivot had been reached, and work in this direction then stopped until the raising and lowering of the leaves for purposes of adjustment had been concluded, after which the girders were completed vertically. The leaves are moved by means of pinions or cogwheels engaging with racks fixed to the edge of two steel quadrants riveted to their two outside girders. The accurate attachment of the racks was a somewhat difficult business on account of the confined space in which the main had to work. To preserve the balance of the bascule, it was necessary to load the shorter or inner arm with counterpoises consisting of 290 tons of lead and 60 tons of iron enclosed in ballast boxes at the extreme ends of the girders. The function of the raising gear is merely to overcome the inertia of the 1200 tons of the leaf and the friction caused by wind pressure on the exposed surface. In designing the hydraulic machinery, allowance was made for a wind pressure of 56 pounds to the square foot, which would produce a force of 140 tons acting with a leverage of 56 feet. The source of power is a building on the east side of the southern approach where are stationed two large accumulators with 20 each rams loaded to give a pressure of from 700 to 800 pounds per square inch. An accumulator is the hydraulic counterpart of the reservoir bellows in an organ. It ensures a steady pressure as its capacity is greater than that of the engines it operates, and since the pumping engines can be constantly at work filling it, there is always a plentiful supply of energy stored against the periodical opening and shutting of the bascules. The water is laid through two 6-inch pipes provided with flexible joints at points of movement to the two sets of engines on the south pier and to those on the north pier through continuation pipes passing up the south tower, across the footway and down the north tower. After use, the water is returned through a 7-inch pipe to the pumping engines placed in two of the arches forming the southern approach to the breach. The engines are duplicated on each pier to avoid the inconvenience that would result from the breakdown of a single installation. The power of the engines is transmitted to the racks through a series of cogwheels which increase the effective pressure of the pistons almost sevenfold. Hydraulic energy is also used to work the two hydraulic lifts in each main tower and to shoot home and withdraw the four locking bolts at the outer extremity of the southern leaf. In this connection, the following extract from Mr. J. E. Tute's fine book on the breech will be of interest. Every precaution has been taken so that the operation of opening and shutting the breech shall be rendered as safe as possible. By an automatic arrangement attached to the hydraulic engines on the piers, they are caused to close the valves which admit the high pressure water just at the end of the operation of raising or lowering the leaves, so that even if the man in charge were to make a mistake through an error of judgment or be prevented from attending to his duties, the leaves would gradually bring themselves to rest either in a vertical or horizontal position without the least chance of any catastrophe. As a still further precaution, however, hydraulic buffers are fixed in such positions that if the man in charge lost control of the bridge and at the same time the apparatus above alluded to for bringing up the motions of the leaves were to fail, their impact would be taken by these buffers, which would bring them to rest in the same manner as that in which the hydraulic cylinders that are attached to heavy guns take up the recoil. In cabins at the east and west ends of each pier are indicators to tell the man in charge whether the accumulators are full before starting the engines and whether the locking bolts are in their proper position. Further provision is made to prevent the raising of the bascules before they are cleared of traffic. The policemen in charge have to stretch a chain across the entrance to each pier. As soon as the chain is fixed, the man carrying it will be able to turn on the water to a small cylinder that draws it tight and at the same time releases the locking arrangement of the levers in the cabin, so that until the chain has opposed a barrier to the traffic, it is impossible to draw a locking bolts at the center of the span. The masonry of the towers is independent of the steelwork that it encloses. In fact, great care has been taken that there shall be no adhesion between the two substances. This part of the structure, carried out by Messrs. Perry and Company, calls for no special attention here, though it impresses itself favorably on the eye of the spectator. Objections have been raised to the external masonry on the ground that it is a hollow sham, but we fancy that were the covering suddenly stripped away so as to expose the steel skeleton beneath, many objectors would be silenced. The general opinion is that with so many metal structures exposing the nakedness of their outlines, the London Corporation is to be congratulated on having thus boldly made a concession to the aesthetic tastes of the community, which does not detract from the value of the bridge as a utilitarian erection. The cost of construction was enhanced, but the result is one of which Londoners will be proud in years to come. The Tower Bridge, typical of modern engineering skill, has an interesting connection with the old London Bridge, itself a mechanical triumph considering the science of the time. Built towards the end of the 12th century, that bridge, which stood the wear and tear of nearly 700 years, was endowed with certain lands which, with the growth of London, became extremely valuable and are now known as the Bridge House Estates. The revenue from them has enabled the Corporation of London to rebuild the London Bridge, throw another across the Thames at Blackfriars, and also to construct the subject of this chapter. We may conclude the account by a few figures. The bridge is exactly half a mile long, including the approaches, the side spans each occupying 270 feet clear. Its extreme height measured from the bottom of the foundations to the summit of the main tower ridge tiles is 293 feet. The roadway of the side spans is 35 feet wide, flanked on each side by a 12.5-foot paved footway. In the central span, the widths are reduced by 3 and 4 feet respectively. Its construction, which occupied 8 years, consumed 235,000 cubic feet of granite and stone, 20,000 tons of cement, 70,000 cubic yards of concrete, 31 million bricks, and 14,000 tons of iron and steel. The columns on the main piers and abutments required 5 miles of steel plates. The total cost was estimated at £750,000, of which the bridge itself represents rather more than half a million. Sir J. Wolfe Barry, the engineer responsible for the construction, includes among his other important works the Great Barry Dock near Cardiff and the completion of the Inner Circle Railway between the Mansion House and Aldgate stations. End of section 5.